Let's look at a couple examples of finding single solutions to an initial value problem. So here's an initial value problem. We have a differential equation x times y prime plus y equals 0. And you'll have to take my word for it that all of these functions, capital A over x, where capital A is just some constant, these are all solutions to this differential equation. If you want, you could pause the video and check that these functions are all solutions. So let's solve some initial value problems. So first, let's solve the initial value problem where we have our differential equation and this initial value, y of 1 equals 2. So to use this initial value, we just need to plug it into the general form of our solution. So y of 1 equals 2 becomes, so we're just plugging x equals 1 into this formula for y of x. We get capital A over 1 equals 2. So capital A is 2. And so the formula we get for this particular initial value problem is y of x is 2 over x. But we need to be a little careful because remember that solutions to a differential equation really only count as solutions where they are continuous. And this function is discontinuous. So let's sketch the xy plane. This initial value right here is really a point in the xy plane. The x value is 1 and the y value is the output of our function y, which is 2. So here. Okay, so when we sketch the graph of our solution, we can only keep the piece of the graph that is continuous that goes through this point. So 2 over x, that looks something like this. And although the graph of this function, 2 over x, does have another piece down in the third quadrant, that is not part of our solution because it isn't continuous with the part of the graph that goes through our initial value. So this solution really only counts as a solution to the initial value problem for positive x values because those are the x values that form a continuous piece with our initial condition. Okay, let's look at another initial value problem. So same differential equation, but a different initial condition. So again, we can plug this x value into our general formula for a solution, which remember was y of x is capital A over x. So plug our x value in there, we get capital A over negative 2 equals 1, and that means A is negative 2 this time. So our solution comes out to be y of x equals negative 2 over x. Now just like before, we should plot this initial condition. So minus 2, 1 is here. And there's a continuous part of the graph of minus 2 over x that goes through this point. But this time it's the part on the left, not the part on the right. This function, minus 2 over x, does have another part of the graph that's in the fourth quadrant, but that's not the part we want because that continuous part doesn't go through our initial condition. So the part we want is the part that has negative x values this time. So to really fully specify our solution, we can write down the formula for it, but also that this has to have negative x values. Okay, let's have a look at another initial value problem. So here's our differential equation, y prime equals cubed root of y, and our initial value is that y of 0 is 0, and I claim that it has this sort of crazy looking solution. Let's graph this solution just to understand what it's really doing. So when x is less than 0, this function is just 0, so it's going to look like that. And then when x is greater than or equal to 0, it's 2/3 x all to the 3/2 power. And it turns out that looks something like this. It's sort of vaguely parabola-like, but it's not a parabola. Something to notice about this is that it's continuous at 0. If it weren't continuous at x equals 0, it wouldn't even count as a solution to a differential equation. So it's good that it's continuous. And something else that we'll notice in just a second is that it's actually differentiable at 0 as well. There's no sharp corner here at x equals 0. To check that this is a solution to the differential equation, we're going to need to calculate the derivative of y. And we're going to have to do that piecewise, since y is a piecewise function. For the part where x is less than 0, the derivative of 0 is just 0. And for the part where x is greater than or equal to 0, we'll need to use some power rule and chain rule here. So the power comes down 3/2 times 2/3 x to the 1/2. And then the chain rule spits out the 2/3 here. The 2/3 cancels that. And that's when x is greater than or equal to 0. So 2/3 x to the 1/2 when x is greater than or equal to 0. All right, to check if this is a solution to the differential equation, we need to compare y prime to the cubed root of y. So that's the cubed root of, let's see, 0 when x is less than 0, and 2/3 x to the 3/2 when x is greater than or equal to 0. And let's see, so now let's do a cubed root for each piece. Cubed root of 0 is 0, and cubed root of this second piece is 2/3 x to the 1/2. And that's for x greater than or equal to 0. This part's for x less than 0. Now comparing these two, yes, those are the same. So this really is a solution to the differential equation. So we have a first order equation and one initial condition, and it has a solution, but here I'm suggesting that there's another solution that goes through this initial condition. And this initial condition is right here at the origin. Pause the video for a second and see if you can come up with another solution. It's actually a pretty simple formula. Okay, so something that might have occurred to you looking at this differential equation is, well, look, if y is 0, then all of this is 0. Right? That's just this flat function that stays at 0 all the time. So another solution is y of x, the constant function, y of x equals 0. So even though in general we kind of expect that given enough initial conditions, a differential equation will have a unique solution, in fact, that's not always the case. Here's an example where we have a first order equation with just one initial condition, and there are actually two solutions that go through this initial condition. In fact, there are infinitely many more solutions that go through this initial condition. They all sort of stay 0 for a while and then jump off of the x-axis like this. So there are actually infinitely many solutions to this initial value problem, which is, it seems unfortunate. And so one thing you might wonder is, are there any restrictions that we can place on the differential equation that would force there to be only one solution to the differential equation? That sort of question is a question of uniqueness. So we've seen that there are solutions exist, but we want to know how could we guarantee that there's only one solution, a unique solution to an initial value problem?